Hello, welcome to module 3 of lecture 7. In the last module, we looked at resource sharing and binding problems with respect to single type of resources. We looked at the register allocation and minimization problem. We looked at the functional unit allocation and minimization problem. We saw that for simple data flow graphs within an operation constraints graph, such allocation can be optimally done in polynomial time by their corresponding interval conflict graphs and using the left edge algorithm. And we also saw that for certain cases when we have loops and branches across operation constraints graph, the resource allocation problem cannot be mapped to simple interval graphs, and hence their conflict graph coloring problems also become NP complete, and therefore enumerative techniques are required to solve them. But we used heuristic graph coloring technique to solve that problem. However, in the last lecture, we dealt with the allocation and mapping of single resource type. In this lecture, we will deal with the generalized resource allocation problems. In the introduction to resource allocation and binding, we said that a certain choice of resource allocation affects further dependent resource allocations. For example, we said that register and function unit allocation choice will also determine the mux choice. Why? Because the numbers of and types of functional units that we have, as well as registers that we have, will determine how many muxes slash demuxes and what will be their type of muxes and demuxes will be determined by that choice. And we said that muxes arbitrate write accesses to registers or functional units. For example, here we have three circuit components, circuit points, which float their output on the registers slash muxes. And the outputs of these registers and muxes again go to circuit components D, E, F. Right? And the demuxes arbitrate read accesses to registers or functional units, and mux demux take up to 40% of the data path, and hence their allocation problems cannot be ignored. With this, we come to the generalized problem. The generalized post scheduling problem may be posed as follows. After scheduling is done, we have a set of register transfers with attached time steps. We know an initial structure of the registers, functional unit, muxes and demuxes say. That means we have done an initial register allocation, functional unit allocation, mux and demux allocation by say our heuristic graph coloring algorithm that we studied in the last module. And for each register, functional unit, mux and demux, we know its cost, and we currently neglect the cost of interconnects. So given this scenario, the integrated post scheduling problem is to find a minimal cost merging on the conflict graph where nodes are the temporary registers and behavioral operations in the schedule. Conflicting register nodes share an edge. Conflicting operation nodes, this is not operator but operation, conflicting operation nodes also share an edge, and each register node shares an edge with each operation node. Right? Now every configuration or state has an associated cost. What is the cost of a configuration? A configuration or state in this conflict graph is a given merging of the functional units, registers, muxes, demuxes. So for a given merging that we have, we will have a total number of functional units required for allocation, a total number of registers required for allocation, a total number of muxes and demuxes required for allocation, and that gives the cost of the configuration. Right? Set of all possible configuration gives the state space of the problem. Now, what the different possible types of mergings that we can do on this conflict graph gives me the gives me the different possible choices that I have and gives the total state space of the problem. A move through the state space generates a new configuration. A move through the state space generates a new configuration, and moves can be generated using either a merge, which is previously introduced. So when we have a merge, what do? We merge two registers together. That means that I am allocating the same register instance to two temporary registers. I am merging two operations together, meaning I am allocating the same functional unit instance to these two operations. So we merge, we introduced previously, now we introduce a split. A split backtracks by one move in the state space and adds to the randomness of the approach. So I can either merge or obtain a higher, obtain a lower number of functional units or registers, or split. That means I have allocated a certain number of temporary registers to a given hardware register set. Then when I do a split, these set of temporary registers will be divided into two sets, and these two sets will be implemented using two distinct hardware registers. Right? So in my problem now I introduce both a merge and a split, and I am saying that each configuration gives me has an associated distinct cost. That means that for this configuration with this merging, then this merging of the different operation nodes and the different register nodes, I will have an associated cost in terms of the functional units required to allocate them, the actual allocations that I have made with respect to the operations, on the operations, the actual hardware registers that I have used to implement the temporary variables that I have, and the number of muxes and demuxes that I will require for this. Now what is the cost of a merge? The cost of a merge is a reduction in cost due to change in the number of registers or functional units. Now when I do a merge, what happens? The number of functional units required to implement a set of operations reduce. The number of hardware registers required to implement a set of temporary registers reduce, because I have done a merge. But on the other hand, arbitration increases, because I have a lower number of registers and functional units. I require more muxes, demuxes for the arbitration. So there can be a possible increase in mux/demux cost, and hence to obtain an overall minimum cost solution, let us say in terms of area, will not be only a reduction, will not be the minimization of the numbers and functional units required. It will be a balance between the increase in cost due to muxes and demuxes and the decrease in cost due to the number of registers and functional units reducing. So we understand that this is again a complicated NP-complete problem, and we can apply different techniques to solve NP-complete problems. Optimal strategies, as we saw, the combinatorial approaches. We can have heuristic strategies. We can also have stochastic strategies. Now currently in this course, we have not studied any stochastic solution approach. So for solving this generalized post-scheduling problem, we will use a stochastic solution approach. So one stochastic solution approach is the simulated annealing. Now the simulated annealing is motivated from the annealing process in metals. So what happens in the annealing process in metals? We heat a solid state metal to a very high temperature and then cool it down very slowly according to a specific schedule. Now if the heating is sufficiently high to ensure a random state when it is heated, so when it is heated at a very high to a very high temperature, its molecules can move randomly and we can have a random state. And then if the cooling is slow enough to ensure a thermal equilibrium, then at the end of the process, the atoms place themselves in a pattern that corresponds to the global minimum energy of a perfect crystal. And with this we obtain large size crystals with low defects. So the basic procedure is to heat the metal to a very high temperature and then cool it down slowly using a thermal schedule, and so that after the cooling process is done we get big defect free crystals. Now this approach was used in simulated annealing. Now simulated annealing is a probabilistic method applicable where finding an acceptable local optimum in a fixed amount of time is more important than finding the global optimum. So simulated annealing approach can be used to obtain good solutions which will not be optimal, but can often be near optimal if enough amount of time is allocated to solve it. It can give you a good solution within a fixed amount of time, and hence this strategy is used. It is an iterative improvement heuristic approach. So it starts with an initial solution and then goes over iterations to find the best solution that is possible for it within a given time. So it starts with an arbitrary initial configuration and iterates in an attempt to bring the system to a state with the minimum possible cost. So therefore, what happens, what it does is, let us say this denotes the state space, this denotes the state space of the problem, and this denotes the cost in terms of energy. For us, energy could be say resource cost, area cost, then performance cost, latency, etc. Right? And we want to obtain, say, the minimum resource design, minimum resource allocation. And we do, how do we obtain this minimum resource allocation? By certain allocation choices for different resources, functional units, registers, and for that we will obtain a certain number of muxes demuxes. So for a given choice of registers and functional units, I will have a certain mux cost, and therefore I will have an overall cost in terms of area. And each point on this line gives a solution in terms of the cost for that configuration. So these are different, each point in this line corresponds to different configurations in terms of which functional units has been allocated to which operations, which temporary variables have been allocated to which hardware registers, right. So that is a configuration, and for that configuration we will have a total functional unit cost, we will have a total register cost, and we will have a total multiplexer cost, and that will give an estimate of the total area that will be required by the circuit. Now basically the simulated annealing process initially partially randomly with a probability moves over the entire state space in search of the global optima. So at each point it sometimes finds the local optima, and then it again randomly chooses the different parts of the state space and tries to ultimately find the global optimum. Now it is not guaranteed that the simulated annealing process will always find the global optimum. However, it is guaranteed that it will find a local, it may find a local minima, but almost always it finds a good solution which may be very close to the global minimum or global optimum that we have. So it is an iterative improvement heuristic approach, and it starts with an arbitrary initial configuration and iterates over the state space in an attempt to bring the system to a state with the minimum possible cost. Let us say in terms of area. So we will now look deeper into the simulated annealing approach. What does it do? At each step it considers moving to a neighboring state probabilistically. So how can it move to a neighboring state? For us it will be a merge or a split. So currently in the conflict graph I have a certain merging over the conflict graph. That means my input is a conflict graph, and then from that input conflict graph I have moved and obtained at a certain time at an intermediate state a certain merging over the conflict graph. That means I have a certain number of operations clubbed together in certain resource instances of registers and functional units. Okay, and that gives me an intermediate state, and that state has a cost, and from that state I can move to another state by either merging another register or another functional unit, or by splitting a current hardware register or functional unit into two different hardware units, hardware registers or functional units with two different sets of operation slash temporary variables in it. So, at each step it considers moving to a neighboring state probabilistically. Moves can be generated either using a merge or a split. Now, what does controlled cooling means? The controlled cooling here in simulated annealing is the slow decrease in the probability of accepting worse solutions as it explores the state space. And why do we accept worse solutions at all? Accepting worse solutions allows for a more extensive search over the state space. For example, suppose I go on doing a merging and I obtain at this local optima. Now, if I do further merging here from this configuration, I will not obtain a better solution. So, I have to randomly perturb the solution and go to a different part of the state space and try to minimize from there. So, but as the solution progresses, now initially I will take the system to a very random state so that I can move over over different parts of the state space, but however, when at later points in time when I'm converging to a very good solution, I don't want to go out of that place and randomly move to a different part of the state space in the later iterations. So initially my probability of accepting worse solutions is high, so that I can move about in different parts of the state space. But as I converge to a good solution after a certain time, after a certain number of iterations, I want to converge to a certain local minimum, which could possibly be a very close to the global minimum that I have. So hence, I slowly decrease the probability of accepting worse solution as it goes on exploring the solution space. So now we look at the steps of the simulated annealing. So we start with a random initial configuration. Fine. Initialize it to a very high temperature. That means I have taken the solution that I have obtained from my heuristic graph coloring algorithm for registers and function units and use that to obtain a random merging. In the initial conflict free graph, we had edges between conflicting operation nodes, we had edges between conflicting temporary registers, and we had edges between conflicting temporary registers and operations. Then we generated an initial solution and initial allocation in terms of an allocation of functional units and hardware registers to the operations and registers, and that gave me a cost of the initial solution in terms of the number of functional units required, the area cost of the number of functional units, the area cost of the registers, and the area cost of the associated muxes and demuxes. Now from that initial configuration, I make moves over the state space. At each move, as I said, I either merge or split. With that merge or split, where do I go? I go to another merging of the temporary registers and operations to obtain a different allocation of the functional units and registers, and we will have an associated mux and demux cost, and that move, due to that move from one state to another, in the current new state I will have another cost of the solution. So we start with a random initial configuration and initialize it to a very high temperature, and then we perturb the configuration through a defined move. So perturbing means I make a move, either a merge or a split, randomly. So that is what do I mean by perturb. Then we calculate score. We calculate the change in score, which is score. For us, the score is the cost. So the area cost of the solution is our score. We calculate the change in area cost or score due to the move made. Okay. Now, depending on the change in score, we either accept or reject the move. So, the probability of acceptance depends on the current temperature that we have. So, we said if the current, if the move results in an increase in area cost, we can still accept the solution in terms of that merge with a certain probability, right? If when the temperature is high, but later we will slowly decrease that probability of accepting higher area solutions. Then we update and repeat. We reduce the temperature and go back to step 2 until we reach a freezing point. Now we will look at the actual algorithm. So initially I have an initial state S0, and that initial I have an initial state S0. I allocate it to S, that initial state, and that state is a configuration of initial mergings of registers, of temporary registers and operations into certain hardware registers and functional units. That is S. That merging is given by S, and that merging has an associated cost which is given by ES. So I stored the state and its corresponding area cost in S and E respectively, and this is the initial state and energy. The energy for us is the area cost. Now initially, because S is the only solution that I have, it's the only merging, and E is the only cost that I have, the current best state and the current best cost is S and E. So I allocate best, S best equals to S, and E best, that is area cost, equals to E. So initial best cost solution are noted here, are given here. Now we have an energy evaluation count. That means basically this is a counter as to how many iterations the algorithm will move through. When will I say that I have still not obtained a good enough solution? When either the energy cost that I have is still greater than an acceptable E max. That means the area cost is greater than the maximum acceptable area that I have. Until this happens, and I have still not exhausted the maximum number of iterations. If I have already got a solution that is acceptable, I can stop the algorithm even before k has reached k max. Right? Now, at any given iteration, the temperature is given by temperature k by k max. So k max is the maximum number of iterations, k is the current number of iterations. So k by k max will initially be a very low value, and slowly k will start with 0, and slowly it will go higher and higher as k increases, and ultimately be 1 if I exhaust all my iterations. If I go over all my iterations, finally k by k max will be equal to 1. So when k by k max is 0, the temperature is highest. So initially I do a temperature calculation, and the temperature is initially very high. So when k by k max is very low, the temperature becomes very high. Now I make a move. Now after I make a move, I get a new solution which is taken down in S nu. So S nu equals to neighbor of S. So from S I make a move, and that move is either a merge or a split. That merge or a split gives me a new solution which is given by S nu, and I have a corresponding energy cost or an area cost which is given by ES nu. Right? Now we accept this new solution. We accept this new solution if P E comma E nu comma T is greater than some random value. If the probability of accepting this new solution which is given by P of E comma E nu comma T, E is the current solution, E nu is the new solution that I have got. If this probability is greater than a certain random value, I accept this new solution. S equals to S new and E equals to E new, and now S and E becomes my new current solutions after this. If E new is less than E best, if the new solution is less than E best, then I have a better solution than the current best that I have. So I need to update E best and S best and E best now. And then I go to the next iteration. So how does this acceptance probability calculated? So P E comma E new comma T is equal to 1 if E new is less than E. So I always accept the new solution if the new solution has a lower cost than the current solution. Otherwise I may still accept the new solution provided this value is higher than the random value here. And what does this value make? When E new is greater than E, that means the new area cost is higher than the current area cost, then this value is 1 by e to the power E new minus E by T. So 1 by e to the power E new minus E by T, this value will be higher when T is very high. So when T is very high, then what happens? When T is very high, then 1 by e to the power this value becomes very low. When e to the power this value becomes very low, 1 by e to the power this value becomes higher, comparatively higher. And then I have a higher chance of this P E comma E new comma T becoming higher than the random. And therefore I have a probability of accepting a worse solution if this value 1 by e to the power E new minus E by T is greater than the random value. So as we said, we always accept a new solution that is better than the current solution. We accept a worse solution with a probability, and this probability reduces as temperature reduces. When the temperature initially is very high, then the probability of acceptance of a worse solution is higher than the probability of accepting worse solutions when I slowly reduce the temperature. If the new solution is better than the best solution that I have, I update the best solution and then I go to the next iteration. And in this process I go on taking moves until I come down and freeze on to a good solution. And after some time, as we said, the probability of accepting worse solution will reduce. We will finally boil down into a local minima, and because of the initial randomness in choosing solutions or in choosing good and bad solutions, there is a high probability of boiling down into a solution which gives me which gives me a very good solution, maybe sometimes the optimal solution as well. And how will the annealing schedule for T, that means how will the temperature change? Initially the temperature, as I said, is set to a very high value, and it is decreased at each step following an annealing schedule, and it ends at T equals to 0 towards the end of the allocated time budget, right? How do we choose whether to merge or split? That is also another question. One choice is that initially I allow splits and merge with equal probability, and then I gradually increase the probability of merges, because finally I want to have more merges than I split. That means finally I want to have a higher resource sharing. I need to obtain a resource sharing that gives me the minimum area cost. With this, we come to the end of this module.